Hello, this is Dr. Asan Abdullah with the course Data Structure and Algorithms, and the topic is sorting, and the subtopic is linear time sort. So, this is the supplemental website www.easymcq.com/goget. So, the course consists of 10 topics which are listed in front of you, and the topic which we are covering is sorting. And of course, the subtopic is linear time sort. Now, this course is supplemented by a very powerful learning management system, which is easymcq.com/, and it has those tremendous 8 features which are shown before you. And those features are covered in 6 videos, 1 through 6. So you can search through all the Q&As, they are properly arranged. You can monitor your progress. You can also set the interface and you can do many things. You can also test yourself. And there are animations which make the understanding very concrete and comprehensive. So I would suggest you to look at the videos. So now we move on to the supplemental website and start with the lecture. We are at the supplemental website, and as you can see, there are quite a few courses available here, such as natural language processing, machine learning, artificial intelligence, and more. But this lecture is focused towards data structures and algorithms. And the mode in which this course and these videos are presented, they reduce the time to cover the content. It is very focused, and there are bullets, and as you can see that it saves a lot of your time. And this content is updated. And let's go ahead and start with it. So we have sorting, and we move on to linear time sort. So the as I mentioned, that the content is in the form of questions and answers, so you know what you should be expecting. So the question is, what are linear time sorting techniques? So there are three fundamental linear time sorting techniques, which are counting sort, radix sort, and bucket sort. And why they are linear time? Because the time taken is order n. So the time complexity of counting sort it is order n plus k, where n is the numbers to be sorted and k is the additional space which is needed to cover the range of the numbers. So how does it works, that I will cover. Then is the radix sort. The time complexity of radix sort is order nk. K here is not the range of numbers, but it is the number of digits within for which the number constitutes the number of digits. And how it works, I will explain, and the key requirements. So if you note that there are key requirements, so these linear time sorting techniques are not generic techniques like the ones which we have covered, like bubble sort, insertion sort, or quick sort or heap sort with time complexities ranging from order n square to n log of n. Those were general purpose, but they have very specific requirements. And for those requirements, they are applicable and they give an order n time. So the counting sort basically is consist of n numbers and k is the range of the numbers. And I will individually go through in more detail. So counting the frequency of each unique element, and then the corresponding location in the array is updated. And so it's updated, and then the requirement is that k must be reasonably small relative to n, otherwise the space complexity of course would increase, and it is best to use sorting integers or discrete values. So if they are not integers and if they are not discrete values, then we need to convert them, and that's an extra effort. Radix sort, n is the number of elements and k is the number of digits. Say for example, typically the year consists of 4 digits, right? So if we are looking at a century, say for example, so we have 100 numbers, right? And each number consists of 4 digits, which is the year. And of course, it depends upon the problem which we are looking at. So the radix sort first sorts with the least significant digit, then the next most significant digit, and then so on the most significant digit. Okay. And of course, the requirement is that integers, they should be integers and fixed length, so that when we say the least significant, then it makes sense for all of them. And when we say most significant, then it makes sense for all of them. For example, if we have a 3 digit number and we have 1 digit number, then the most significant and the least significant is 1 for the 1 digit number. But for the 3 digit number, the most significant digit is the leftmost third one. Performs best with integers of fixed lengths on strings, and linear if the number of digits, right? So then we have bucket sort. Bucket sort time complexity is again order n plus k, where k is the number of buckets, n is the number. So what happens is that the numbers corresponding to the numbers we have buckets, and each bucket has a different range, and the values go into the bucket, and then those values are sorted. Okay, and of course they have to be uniformly distributed. If they are not uniformly distributed, then what's going to happen, that the simple sorting techniques that may result into quadratic time complexity. So all that effort gone and for nothing. And of course this is the reference. So what is counting sort and how does it works? So this is the explanation of the counting sort. Find the range of the input. For example, you take the difference and create a count array in which the numbers will go populate the count array, and you cumulative perform the counting and then place the elements. So the time complexity is order n, and the space complexity is order n plus k. So you can read this, and but as the saying goes, that a picture is worth 1,000 words. So let me cut on the words and go to the picture. So you see that this is the given data set. So we have 1, 2, 3, 4, 5, and 6 numbers, and the range of numbers is from 1 to 8. Now, if you count this additional space, this space consists of 9 spaces: 1, 2, 3, 4, 5, 6, 7, 8, 9. The reason being the counting started from 0, and the number corresponding to the range was 8. So 0 to 8, we have 9 locations, and this is the ninth location, which has the address of 8. So what happens in counting sort, that the numbers, okay, corresponding to their location, they are sent there. They go there. Of course, the frequency count is also done. And when we this a step here which is cumulative count. So after this step of cumulative count, what we get is these spaces are then they are not taken into consideration because we don't have a number corresponding to these indices. Basically, these are the indices. So we have this result. And you can see that this is sorted. So this is how counting sort works. Now, what is bucket sort and how does bucket sort works? So what we do is, first of all, we initialize the array, okay, determine the range of the input data, and then create an empty buckets and distribute. Then we send the numbers corresponding to their buckets, and then the sorting takes place for a bucket, and then there is a concatenation. So again, if you look at this picture, which is more than 1,000 words worth, so these are the numbers to be sorted, okay, and of course they are not sorted. So we have these three buckets. And in the subsequent example, I'll show you with a very concrete example how these buckets are utilized. So these seven occurrences, multiple, go to the first bucket, then the next bucket, the 8 occurrences, which are two of them, and then the ninth. So as you can see that if we concatenate these buckets, we get a sorted result. This is the sorted result. And as can be seen that this is stable sort, because the relative order of these two sevens is actually there are three sevens. Those three sevens is maintained. So let's look at the pseudo code for bucket sort with a concrete example. So we have a set, and so how are we going to assign the bucket? The bucket is going to be assigned based upon the number and the index, right? The number and the index. So say for example, if the bucket size is 10 and the number is 0.42, so how are we going to get it? Which is 10 into 0.42 the floor. So that's how we get the index. So we have this set of numbers, and these numbers are basically, say for example, we have 0.23. So 0.23 multiplied by 10 is 20, is what? 0.23 into 10 is 2.3. So we take the floor and we get the address 2, and it goes to the bucket 2. Similarly, 0.29 also goes to the bucket 2. As you can see that for bucket 4 there are 3 occurrences. Bucket 0 there are no occurrences, and these numbers within a bucket, they are not sorted by any chance, but they actually sorting was performed. So when we concatenate these buckets as we did earlier, so we see that 0.23, let me show you what is meant by concatenation. So concatenation is, this is coming to here, and this is coming to, this is how the concatenation takes place. So this concatenation, so if we continue with this concatenation, this results in the sorted results, which is shown here. Okay, so this is how it gets sorted. So what is a radix sort and how does it works? So the radix sort is again a stable sorting technique, and we sort digit by digit. First we sort based on the least significant, then the most significant, and so on, and determine how do you determine the maximum number of digits, which is the number of digits in the number. Okay, and then sort by each digit. To first pass the least significant, the second pass the next most significant, and so on until it is sorted. So for example, if we consider number 802, which has 3 digits, so the least significant digit is number 2, then is number 2 at the first position, number 0 as a second position, so it will have three passes. And of course, I will explain it to you using an example. So let's consider this example of sorting these six numbers using radix sort. Now we demonstrate the working of radix sort with a concrete yet a simple data set, which you can see on the screen. So we basically what it constitutes is the first pass on the least significant digit, units place, then the second pass on the tens place, and then the most significant, which is the hundreds place. And we'll be performing radix sort using the counting sort. So I'll go in detail over one pass, and the remaining two are also present in this Q&A, which I will not go over, but they are same to it. So these are the numbers, and this is the order in which the numbers were given. So we look at the least significant digit, and that is listed here. And then we perform the counting sort. So we declare the array of size 0 to 9. So the size is 10 because we have a 9 here, and the counting is starting from 0 index. So we increment based upon whatever was occurring, right? So this is what we have. So 0 occurs twice, 0 occurs twice, 1 occurs once, and 2 occurs once, 0, 1, 2, 3, 4, 5 occurs once, and 9 occurs once. So convert this to a cumulative sum, okay, which is here. So cumulative sum 2 plus 1 is 3, 3 plus 1 is 4, and 4 plus 0 is 4, 4 plus 0 is 4, 4 plus 1 is 5, and so on. And then we use the cumulative count array to put them into their respective digit position. So this is what we have. This is the first pass. So after the first pass, this is the sequence of the numbers. And then we do the second pass. After the second pass, this is the sequence of the numbers. And after the third pass, it gets sorted like this. Okay. So if you look at this figure, so we can see that these are the numbers, the least significant which we are referring to, and the sorting takes place on these least significant numbers. So the least significant was 0 and 0, so 900 and 770 come at the top, and this is repeated till we get the final array. So what are the limitations of linear time sorting? It looks like to be wonderful, and it is, but of course there are limitations also. So the limitations are limited applicability to specific data types. What are those data types? The data types have to be integer or categorical, the floating point numbers. Radix and bucket sort are typically designed to handle fixed length, because we were sorting based upon the least significant, then the units and tens and hundreds. So if the numbers are of not the same, we will have to bring them to the same digit size. For example, if they are in real number, we need to multiply them or need to add them. If the numbers are negative, we need to add something. Space complexities, they take space. For example, counting sort requires order key additional space. Radix sort also requires space, and that space and bucket sort also requires the range of the values. Performance dependent on the range of input. So if the range is large, right, then there are more operations to be performed. When we say order n plus k, so there are more operations to be performed. And if the large number of broad range of values, linear sorting can be far less efficient than comparison based sorting, far less efficient, because the number of operations increase. Inability to handle comparisons directly. If for the example, if for example, there's a requirement of comparison, okay, uh, sorting based on custom comparator, so that comparison is not there in linear time sort. That is not allowed. And so it's a not comparison based, difficult with negative numbers, as I mentioned before. They must be shifted to positive values by adding an offset. So if I have -6, so maybe I add offset of 6 to make it a 0. Then that offset 6 has to be added to all the numbers, which will increase the range and other complications. Limitations of large data sets with uneven distribution. So if the distribution of the numbers is uneven, say it's Gaussian, right? So then in that case, those buckets which have more numbers, or if they become proportional to n, so it will deteriorate to order n square. So these are some of the limitations. I would suggest you to read this more, and that's for all this topic.